This is part 2 of the 5.07 equilibrium recording. Determine the equilibrium expression for a reversible reaction. Suppose you are given the chemical reaction shown at the right. How would you go about determining its equilibrium constant? So we have 2CO plus O2 is in a reversible reaction or yields 2CO2. Remember that the equilibrium expression is the ratio of the concentration of products to the ratio of the concentration of reactants. So the products go on the top. Where did this 2 come from? From the coefficient in front of the CO2. On the bottom we have our reactants, CO and O2. And where did this 2 come from? From the coefficient in front. That being said, I want to make a note about this. Here we go. When I said it can be to chemical A and then to the power of its coefficient times the next chemical. And I had it in a different order. I had A and B on the top and C and D on the bottom because really A, B, C, D can mean your products or your reactants, but I should have done it in the same order they did, so I switched it. So now on the top I have chemicals C and D to hopefully remind you that that's the product over the reactant. So if that caused confusion, sorry about that. You are ready to calculate the equilibrium constant for an equation. Start with this equation. N2 plus 3H2 yields 2NH3. This equation represents the reaction for the product of ammonia, a reaction known as the Haber process. Nitrogen gas and hydrogen gas react to form ammonia gas. Ammonia is an important component of fertilizers. The reaction reaches equilibrium with the following concentrations. So for N2, there is 0.8 molar. For H2, there's 0.6 molar. For NH3, there is 1.7 molar. How do you find the equilibrium constant for this reaction at this temperature? So if you can do it, hit the pause button and go through and do it. If you're not there yet, that's okay. Remember, you want to start with the concentration of the products over the concentration of the reactants. So you do need your balanced chemical equation. Okay, so you need your balanced chemical equation. And then you have your products to the power of 2 over your reactants, the N2 times the H2 to the power of 3. Where did this 3 come from? From the coefficient in front of it. Remember, the exponents come from the coefficient in the balanced chemical equation. Then plug in the numbers. So instead of writing NH3, what number would we put? We would put 1.7. So 1.7 squared over the concentration of N2, which is 0.8, times the concentration of H2, 0.62 the third power. Make sure you cube it first and then multiply by the 0.8. So put in the numbers, put it in your calculator, and you should get 16.7. Please put this in your calculator. Make sure you get the right answer. Sometimes people just don't know how to use their calculators correctly and you get it wrong even though you set it up correctly. Alright, so it gives you an answer of 16.7. And if you're like, okay, great, whatever, right? Well, that actually means something. The equilibrium constant can reveal the nature of the chemical reaction. So it tells you if it goes to the right and creates more products, or goes to the left and creates more reactants. The equilibrium constant is always a positive number. It can range from extremely small to extremely large. What does the value of the equilibrium constant tell you about a reaction? If a reaction creates far more products than reactants, the numerator is large and the denominator or bottom number is small. That means equilibrium constant will be relatively large, and equilibrium exists when the far right of the reaction is favored by nature. By contrast, if few products form and many reactants remain, the numerator is small and the denominator or bottom number of your fraction is large. So relatively small equilibrium constant means that equilibrium is far to the left. Okay, so the one we just did, the equilibrium constant for the Haber process for making ammonia gas is 16.7. This is a large number, and it indicates that the products are favored. So in other words, there's going to be more products, there's going to be more of the NH3 than there's going to be of the N2 or the H2. Alright, and I'm not sure why, this picture is from a previous one with the hydrogen iodide gas. Okay, so before we go to that, I just put in my notes, the equilibrium constant is always a positive number. If it's small, there we go. If it's small, it creates more reactants So equilibrium is to the left. If it's large, it creates more products. Equilibrium is to the right. In chemical equilibrium, the products and reactants of a reversible reaction remain constant over time. Reversible reactions reach chemical equilibrium if the rate at which the products and reactants are produced remains in a dynamic consistency. So meaning even though it's going back and forth, the percentage is the same, the reaction is at equilibrium. Equations at equilibrium can be described quantitatively or with numbers in terms of their equilibrium constant. Chemical reactions are reversible. They may proceed forward. They may proceed backwards, but they can be in chemical equilibrium and are described by the equilibrium constant. And that's it. As always, if you have questions, let me know.